I saw it.
Go to slideshow from the beginning.
Slideshow from the beginning.
Left.
There you go.
Alright, sick. So, Jerome and I have had an all-night rave, like it says in the title. This is me, that's Jerome. Oh, sweet. Alright, so our purpose was to discover how changing the frequency in a module wave of light in a speaker system will affect the resulting laser pattern. And I'll show you more in the diagram of what that setup was. And our hypothesis was we really didn't know going into the experiment what we would find and kind of like what data we would collect and what graphs we would. So it was kind of like just exploring the universe. And so this is our setup. This is Jerome's basement. And so it's really small, I'm sorry, but there's a laser pointer right there. And we attached a small mirror to a speaker right in the center of the, I don't know what you call it, the
speaker cone.
Speaker cone? There you go. Speaker cone. And so when we played the speaker at a tune, which you'll hear later in the presentation, the mirror vibrated. And so that pattern of vibration created a design on the ceiling around up here. You kind of see in this picture, this is the view from the laser. The laser went like this, and then went up to the ceiling, just like that. And so what we did is we played a frequency in different waves. We had a sine wave, a square wave, a sawtooth wave, and I think I'm forgetting one, but it'll come up. And so we played those different kinds of waves, and we increased the frequency of each wave, and you'll see those graphs as according to time. Alright, so the procedure is pretty quite simple. We use a computer program in order to get different wave functions and get different frequencies. So as far as steps go, it wasn't that hard. We simply videotaped the resulting laser pattern on the ceiling, and that was our data, and we performed video analysis on it through position. Alrighty, so hopefully this works. So this is our control. This is just the speakers playing 100.
On.
Alright, so if you guys remember kind of what I was talking about, was it like 2 days ago? We had a laser. Let me just try to draw it really quick. So we had a setup like this. We had a laser right here, not drawn to size. And we had a speaker right here. And the laser hit the speaker, and there's a little mirror right here. Hit right there, and go up to the ceiling. And it projected an image, which you'll see soon. And so we played a frequency and a wave through this speaker, and we did different ones. We did sine, square, triangle, and a sawtooth. I think that was it.
The wavelengths, right?
Yeah, those are all different kinds of wavelengths. And so this is our control. This is just plain, just 100. Let's see that. Alright, so yeah. Give me a second. Okay, well the sound's not working, but
You can turn this.
The sound on the thing is turned off.
that's why.
There's sound.
So you can see how it elongates and stuff. You can also hear me. So this is just our control.
About how big is that laser, like the dot? Is it just like a regular?
Yeah, just like a regular laser. So you can see we were finding different patterns. And so now I'll play the sine wave. And these got really interesting as we went on. So what we did is we measured the displacement that it was going, and so we used a video analysis and we would measure the x displacement of it.
Oh man!
So they got started to get really crazy, and this was just, I'll talk about it a little bit later, but we were getting interesting stuff with just one speaker, and so our original lab was like going to be 2 speakers, but we were getting stuff with this, and so it was So that was the sine wave. And then here, let's do a triangle wave. And then, so one of the times our mirror bounced off our speaker, so we had to do it a different day. And this is obviously a little bit in the daytime. And so this is what is this? Triangle wave.
Yep.
So you can see that the laser is obviously affected by the wave that's going through it. And this is the mirror vibrating at different waves and different frequencies. Alright, let's get through these really quick. Let's do square wave, and then we'll do the sawtooth. The sawtooth sounds terrible.
100.
Huh.
Alright, and last but not least, let's do the sawtooth. That's the source of error. Alright, so we were getting some pretty cool stuff. Obviously, it can be like something you see in like a laser show or something. And so, it was really interesting to me also because there's something called like a Lasages waves and like kind of patterns that you can make, and they there's displacement in the X, Y, and Z direction with two speakers. We only use one speaker, and we still got displacement in the X direction, so we mainly focused on that. Let me get to. Sorry, guys. I don't know why it wants to do this.
I think what happened is you embedded the videos inside the PowerPoint,
And that's
which made the PowerPoint huge.
Yeah.
So-
Oh, that's almost done.
The safest way is to make a link, or just pause and
Next time.
yeah, next time.
So, how do you guys get this idea, by the way?
Jerome actually looked stuff up, and so I can actually talk about this is loading. So there are things called there's a parametric equation, or parametric equations. We didn't do anything with that, but it's where my uncle does something with it, and he knows some stuff about it. But there's
He does some things.
but
Stuff happens.
there's two functions in this one equation, and so it's pretty confusing, but there's like almost two like ways the equation can be true. If I'm saying it correctly, I hope I am.
Like a quadratic.
I don't know, Doc, do you know anything about?
Yeah, that's cool. Parametric equations, two equations that govern a single relationship.
Yeah.
They're sort of like nested equations, kind of.
Yeah, so then that's what those two speakers would do if we would have used them. It would have been almost two equations combining, and then that would have formed that image. Alright, so let's get to work here. So these are all the videos. Okay, so this is what each wave looked like that was coming out and using like vibrating in the mirror. Sine wave, square wave, triangle, sawtooth. They all look like what you would think they would look like. And so, in our following graphs, so this was our control graph. We didn't really know kind of what to make of this. It was just, you could see it kind of increasing, but it was very weird. But this is X displacement right here. And so we measured using linear analysis how much it was elongating each time over time. Alright, so here is where things got pretty cool. So when we did our sine wave, you can see that the displacement was similar to a wave. So the way the laser was elongating and displacing in the x direction was also related. It was directly correlated to the wave that was being emitted. So like for this triangle wave, you can see there's a distinct point. So it goes jets up, jets down, jets up, jets down. And so we are finding that the displacement made by the wave was, by the light, was the same as the wave that we were emitting. And so this is the square. You can see the square pattern. And obviously it decreased a little bit. And then for the sawtooth, it's right there. You can see like the jagged lines. So yeah, so that's kind of our finding. We found that the displacement of the laser was the same as the wave that we were emitting, which was very cool. Obviously, if we added a second speaker into there, it would have added almost it would be a parametric equation, and it added another function of a wave into there, and we could have gotten numerous designs and kind of displacements. So sources of air, the mirror, the biggest problem was we used like wood glue or something like that. We tried to get the stickiest glue possible, but there was still some extra vibrations probably between like the wooden speaker. So like the mirror would reverberate against the speaker, so it would add like a little bit more vibration than what we wanted, instead of just following the vibration of the speaker. Let's see. Others could be just simple light interference from like outside or anything like that. But other than that, I mean, I think I found usually with light labs you don't have a lot of air, and if you do, then it's pretty noticeable. So in the conclusion, I was kind of talk about how the wave emitted related to the displacement of the light on the ceiling, and that's what we found. It was pretty interesting. It was pretty cool. So thank you. Any questions? Oh, sweet. Alright, so our purpose was to discover how changing the frequency in a module wave of light in a speaker system will affect the resulting laser pattern. And I'll show you more in the diagram of what that setup was. And our hypothesis was we really didn't know going into the experiment what we would find and kind of like what data we would collect and what graphs we would. So it was kind of like just exploring the universe. And so this is our setup. This is Jerome's basement. And so
I saw it.
Go to slideshow from the beginning.
slideshow from the beginning.
Left.
There you go.
Alright, sick. So Jerome and I have had an all-night rave, like it says in the title. This is me, that's Jerome. Played the speaker at a tune, which you'll hear later in the presentation. The mirror vibrated, and so that pattern of vibration created a design on the ceiling around up here. You can kind of see in this picture, this is the view from the laser. The laser was really small, I'm sorry, but there's a laser pointer right there, and we attached a small mirror to a speaker right in the center of the, I don't know what you call it, the
Speaker cone.
speaker cone. There you go, speaker cone. And so when we